I'm sure you're familiar with force. So, what is your understanding about force? What is force? Force is, yes. Right. So, it is an external cause, okay, which affects change in state of motion or the shape of the body or its direction. A change in shape only if the body is non-rigid. The body is rigid, then there will be no change of shape. Okay. So basically, it is an act of push, pull, or kick by an external agent. Act of push, pull, or kick by an external agent. Or a body. This is force. What is the effect of force? Effects of force. It changes the state of rest or motion. It changes the state of rest or motion. Motion, to be specific, you can say uniform. Because rest and uniform motion are similar in some sense. What is common in a body at rest and a body in uniform motion? Is there anything common in them? Huh? They are constant. What is constant in them?
Like in the state of rest, the body doesn't any function, the body in the state.
So how do we specify? What is common in them? Are they accelerating?
Velocity.
Are they accelerating?
No.
No. When the body is at rest, acceleration is 0. Even in uniform motion, the acceleration is 0. Okay, so they are the state of motion with 0 acceleration. And by Newton's second law, whenever the acceleration is 0, what about force? 0, because force is mass into acceleration. Yeah, therefore, force is also 0. So when a body is at rest or when it is in uniform motion, there is no force acting on the body. Okay? When the force will act, then it will change the state of rest. The body from rest will begin to move. So there is acceleration, change of velocity, zero velocity to some velocity. Likewise, if the body is in uniform motion, yes, it will either accelerate or retard. Correct? If the body is in uniform motion, when the force acts on it, let's say body is moving in this direction, force also acts in the same direction and it will accelerate. If the body is moving in this direction, force acts in opposite direction and it will retard. Okay? So this is what force will do to the state of rest or to the state of uniform. Okay. Or uniform. Is that clear? Okay, next. What else it can do? It can change. Yeah, it will changes the shape and size of the body. Only if body is non-rigid. Okay, it will change the shape and size of only non-rigid bodies. For rigid body, we'll see what happens to rigid bodies. What else it can do? It can change the direction of motion. right? Even if the body is moving with the same speed, but you need a force to change its direction, right? So changes the direction of motion. Right? So these are some of the things that force can do to a body. Now, very specifically, let us discuss this effects of force on rigid bodies. So, pre-rigid body. Let's discuss this now. So, can we treat duster as a rigid body? Right? So, what happens when the force is applied? It is moving in the direction of force. Right? So, force causes linear or translational motion in a pre-rigid body. Right? You see here, if you have a pre-rigid body, the force is applied this direction. The body will begin to move in the direction. So force causes linear or translational motion. Its direction. Okay. So motion takes place in the direction of force, but it is linear or straight line motion or translation. One and the other. Okay, so I'll erase this. These are just the topics. We'll come to it one by one. Next is effect of force on a rigid body fixed at a point. So if a body is fixed at a point, that fixed point is also called as pivot. Or if it is a door, for example, it is fixed along the hinges. So you can also say axis of rotation. Body can be fixed at a point like this. Fan is fixed at one point, so it is rotating about this axis, right? So axis of rotation. So whenever any object is fixed at a point, let us say the wheel. And now the force is applied here. And this is the pivot. And what will happen? It will cause turning effect. Okay? It will begin to rotate. So force will cause rotational motions. So about the pivot. Force will cause rotational motion about the pivot. Okay. This is what we have. So we have just seen two cases. When the body is free, it will undergo linear motion or translational motion in the direction of force. Whereas in this case, the body will undergo rotational motion about the fixed point or the pivot. Right? So if it was a door, for example, the hinges here. We have a handle here, let us say. So if a force is applied in this direction, what it will do, it will turn the door towards right. Door will open in this side. Okay. And you push the door inside. Or when you change the direction of force, pull, then it will rotate in the other side. So this is anti-clockwise. During the push. So two motions are possible, either anti-clockwise or clockwise. Turning effect is only these two, clockwise or anti-clockwise. Okay. How do we measure this rotational motion? It is measured in terms of what is called as moment of force. Okay. Rotational motion is measured as moment of force. Expressed in terms of moment of force. So whenever the word moment comes, it means it is talking about the rotational motion. Measured or expressed in terms of moment of force. It is also called turning effect of force. Or it is also called torque. These three things are one and the same thing, interchangeable. Moment of force, turning effect of force, or torque. And the symbol for torque is this. Okay. It is curly T and it is pronounced as tau. It's a Greek letter pronounced as tau. So let's consider some random rigid body of any arbitrary shape. And imagine this is the pivot or the fixed point. Imagine some potato and you have pierced a needle. Okay, something like that. And let us say that at this point you are applying the force. This is the point of application of force. What is the line of action of force? This represents line of action of force. Where is the fixed point? This is the fixed point. Who is the axis is passing? Okay. So if I take the example of door, so if I pull this door, what is happening? It is rotating about the hinges. Right? Now you see that when the handle is away from the hinge, then the effort needed is minimum. Okay? If I shift this handle closer to the hinge, I'll have to apply greater effort to open the door by the same amount. If the handle is at the hinge, then it won't rotate at all. Right? So what does the turning effect depend on? It depends on two things. One is the magnitude of the force applied, and also the point, the perpendicular distance at which the force is applied. It depends on two things. There will be no turning effect if the perpendicular distance is zero. Clear? So how we define the moment of force or torque? It is defined as product of the perpendicular distance. Let's call this point as OA into the magnitude of force. This is how moment of force is defined. Okay. That is, moment of force is equal to product of perpendicular distance given and line of action of force. Magnitude of moment of force is obtained by multiplying the perpendicular distance of force and the pivot times the magnitude of force applied. Okay, so this is perpendicular. What is the sense of rotation in this case? What is the sense of rotation for this case? How will it rotate? It will rotate like this because I'm pushing. So what is it? Anti-clockwise. So direction. Now, moment of force is a vector quantity. So it has the value, the magnitude, and also the direction, anti-clockwise or clockwise. And sign is taken as positive. Okay, suppose multiple forces are applied. Some people are trying to open the door and some from the other side are trying to close it. Then the door will rotate in the direction of net torque. Okay, so in that situation, when multiple moments of force are acting, then you have to algebraically add it. So clockwise is taken as negative. Okay, it is a convention. Always anti-clockwise rotation is positive and clockwise is negative. Throughout the world, this is obeyed. Now look here. If I apply some force here, so I'm applying two forces now. So it is anti-clockwise or clockwise? Anti-clockwise. Where is it moving? Up. That is the direction of positive y-axis. So anti-clockwise advances in positive y-axis. Clockwise, right. Throughout the world, this is called the screw rule. Okay. So right hand screw rule, right? So always the anti-clockwise direction is positive and clockwise direction is negative. Same holds true with the angles. Now, suppose you make angle, this is a circle, right? So this is 0 degree. Now, when you turn it anti-clockwise, then it becomes 90 degree. So angle increases. So this is positive angle. Okay? This is positive. Anti-clockwise direction is always taken as positive angle. This is plus 90 degree. Okay? Now if you turn it clockwise, then angle reduces. So that is negative direction. The two ways you can remember. So it is true for angles also. When the radius vector is rotating in this direction, the angle is positive. And when you are going in this direction, the angle is negative. Same rule throughout. So note, moment of force is a. So somewhere I read moment of force or torque. Torque is a vector quantity. It has both magnitude and direction. So in numericals, right, wherever possible, let us specify both magnitude as well as direction. If you only state magnitude, no direction, then your marks will be cut. Okay, so we'll see in numericals. Now let us discuss the units. So tell me what will be unit of torque? It will be unit of distance multiplied by unit of force. So what is unit of force? Newton. Distance is meter. Okay, so this is SI. SI system mein the unit is Newton meter. In CGS, what is the unit? Newton becomes dyne. Meter becomes. What is the relation between Newton and dyne? 10 raised to 7 or 5? So because what is Newton? Newton is 1 meter per second square, right? Into kg. Mass into acceleration. So mass is kg. Kg meter per second square. So this becomes how much? 1000 gram to 100 centimeter per second square. So gram centimeter per second square is dyne. Okay. So this is what it is. Gram centimeter per second square is dyne. 1000 into 100 is 10 raised to 1. So this is the unit of torque in SI and series. Then you also have gravitational units. So you have so in gravitational unit, force is represented as kilogram force. Kilogram force meter. kgf meter. Okay, that is the gravitational unit of moment of force. And in so this is in SI. In CGS it will be GF centimeter. Okay, and you know kgf to Newton conversion. How much is 1 kgf in Newton? 9.8. You multiply by G. So this kgf becomes equal to how much? 9.8 Newton meter. Here it will become 980 centimeter. So these are some of the unit conversion that will be handy for solving numericals. Okay, gravitational unit also have SI and CGS counterpart. Just the Newton becomes kgm. Okay, that's the only thing. And I think you've already studied in 9th about this. I'm just repeating it for class. So note down till here, and if you have any doubts, you can ask for proceeding. Okay, you have signed it. Let's discuss some examples of movement of force from daily life. The one very obvious is opening or closing of door. Yes, steering wheel. Steering wheel or wheel. Okay. So you turn it or the engine turns it. Yeah, that is also there, but that becomes more complicated. The steering wheel is like you are turning it of a toy or a car. So turning of a steering wheel. So are these two similar or different? Is there any difference? To turn the door, just one hand is enough. Correct? So you can just with one hand. What about wheel? Huh? You can turn it with one hand also, but generally for more convenient rotation, we use both hands. So we apply equal and opposite forces. Yeah? Same holds true for opening or closing the bottle cap. So and where is the pivot here? This is the pivot O, right? Now you see two equal and opposite forces are applied at the opposite ends of the wheel, diametrically opposite ends of the wheel. So you have a pair of forces. So it has a special name, it is called couple. The turning effect is produced by a couple, a pair of forces. Couple means a pair of forces. Equal and opposite forces. Acting at different points. So couple is a pair of forces acting at different points. That will produce turning effect. Clear? Here also, in case of a bottle cap, also you will require the forces in two equal and opposite directions. Right angles. Here also you see that there is some separation. There is some perpendicular distance between the two forces. So that is got a special name. It is called couple. Okay. So door, can you have one more example where you apply a single force and produce the turning effect? Lego, have you done this tightening or loosening of a nut with the help of a wrench or spanner? So that is also there. Pedaling a bicycle, that also produces rotational motion of the wheel. There you have a couple. Four. Tightening or losing nut. Using spanner. Wrench. So in case of a spanner, spanner has a lever and the nut is somewhere here. Okay, so this is the fixed point O and this is A. So you can either apply the force in this direction to loosen it or in this direction to tighten it. You must have seen a wrench like this. They have a but now you can, use both the hands. Okay, you have different slots. There is also a cross, right? So different size of nut you can open, right? Go to a cycle garage, you can see this. So wrench you will apply couple, whereas spanner you apply single force. Can you really apply a single force? It looks that on the door you are able to produce turning effect with a single force. What is Newton's third law? So forces always act in pairs. Even if you are applying single force, but actually it is generating a reaction force, right? So when you're opening or closing a door, you are applying the force at the handle. The equal and opposite force is applied on the hinge as a force of reaction, right? But that reaction force is not producing any turning effect because there is no perpendicular distance. It is acting at the pivot. Got it? So that's why for convenient rotational effect, you apply couple. There the rotation is more convenient. Got it? So couple produces better turning effect than just a single force. Because now both the forces are producing moment about the pivot. And you see that couple produces rotation in the same direction. So whether positive or negative, their magnitudes will be added. Understood? So now let us calculate the moment of a couple. So everywhere, if this is the force of reaction will be here. This is the reaction. This is action. Although so this force will produce the moment, but this will not, because this is a fixed point. Here there is a perpendicular distance OA for this force. But the perpendicular distance for this force is 0. Clear? So force is always acting pair. Just keep this in mind. Now, so for moment of a couple, I told you that there will be two forces. Let's say this is the, like if you take this example, just the force diagram. So this will be O, A, and B. Okay. So these are the forces acting in a couple. So what is the moment of a couple? The moment of the couple is equal to this perpendicular distance AO. Let's call this F1 and F2. Now our F1 and F2, F1 is equal to F2 is equal to F, say. Because in magnitude the forces are same. Okay. So moment of couple is equal to moment produced by the first force about O plus moment produced by second force about O. And they are equal, so this will be this becomes AO plus OB. Yeah. This becomes AB. So this is what it is. So this is also torque only. What is the difference? Now it is the product of the perpendicular distance between the forces of couple times any force, either force of the couple. This is the definition of moment of a couple. Okay. So moment of couple is equal to of perpendicular distance between the forces of couple magnitude of either force. Moment of couple is also called torque. So it is also torque. Turning effect is torque. So the two torques are added because they are both producing anti-clockwise rotation and both are positive. They will be added. This distance AB is also called as couple on. And this distance OA is called moment arm. These are some of the nomenclatures you might come across. Okay. So in this diagram, this is the moment arm. The whole thing is couple on. Let me know if you have any questions. You see, you're using books from different publications also. Selena as well as Evergreen, right? Any other publication apart from Selena and Evergreen? This is others. That's not Evergreen. But you might be finding all the topics similar. If there is anything in your book you're not able to understand, you can ask. Okay, is that clear? So we are going as per the prescribed syllabus by ICSE. Okay, so most of the topics should be common in every publication. Okay. So far, so good. Any questions till here? So next topic is equilibrium of bodies. So what is word equilibrium signify in general? Balance or stability, right? We need mental stability. So in life, what we need is equilibrium. So likewise in physics, let's say if you're traveling in a car, what would you prefer? A bumpy, accelerating, braking car or a cruising car? Huh? A cruising car would be a preferred choice, obviously, because that will be a stable riding experience. Correct? So, how do we define equilibrium in physics? So, when there are multiple forces acting on a body, multiple or multiple torques acting on a body, then too, if the state of motion of the body is not affected. You get it? When a body is subjected to multiple forces or torque, right? And that is not changing the state of motion of the body, either its state of motion or its rest. Then the body is said to be in equilibrium. Got it? So, body is said to be in equilibrium. Its state of rest or of uniform motion is unaffected while it is subjected to multiple forces or movement of forces. Okay? Multiple forces and or movement of forces. Does it make sense? But it is. Multiple forces and or movement of forces. It is and or. And or. So this is also multiple. Multiple forces and or movement of forces. Make sense? So there are two types of equilibrium of bodies. Types of equilibrium of bodies. One is static equilibrium. So having understood what is equilibrium condition, so in static equilibrium, the body in equilibrium remains at rest. Body is in equilibrium and also in rest. So when the body is in equilibrium, that means it is subjected to multiple forces or movement of forces. While experiencing all those forces and movement of forces, the body is at rest. Then it is said to be in static equilibrium. So what is static equilibrium? Body at rest while in equilibrium. Okay, so what are the examples of static equilibrium? Can you think of examples of static equilibrium? What about the book lying on a table? Is it at rest? Is it in equilibrium? What are the multiple forces acting on the book? Gravity and reaction. So multiple forces. Is the book rotating? No, so there is no rotation. So one example is book lying on a table. Any other example? Static equilibrium. Game of tug of war. Right? Both sides are able to exert equal forces. Then will the rope move anyways? No, right? So you can say when an object is subjected to two equal and opposite forces on either side. So will the block move anywhere? No. This is also a case of static equilibrium. Balanced forces, right, on both sides. Then the next is, so we have just a minute. So next case is dynamic equilibrium. So here the body remains in uniform motion while in equilibrium. In this case, while in equilibrium. Okay, we'll see the examples after the break.
आई कार्ड सबको मिला है सबको मिला है आई कार्ड क्या है आपको यहाँ क्या नाम है ब्लैक शर्ट ब्लैक टी शर्ट क्या नाम है हाय नहीं मिला है क्या पहनो ना कबीर आर्या, अनन्या, रेयान,
Can you think of examples of dynamic equilibrium? An object moving with a uniform speed. And is also there. Yes. With uniform velocity or constant velocity. What about fan? Has to be uniform, right? So fan uniform velocity or uniform speed? Uniform. Rotational में क्या होता है? Velocity keeps changing. With uniform speed. Pulse. What about plane flying at uniform speed or uniform velocity? With equilibrium case, dynamic equilibrium, plane is in motion. So देखो, so its weight is downwards. Which force is balancing its weight? Upthrust. Upthrust due to air. And if it is moving with constant velocity, so there is no acceleration in forward direction also. So there is no force in horizontal direction, no net force in vertical direction. So it is a equilibrium. Is the plane rotating? So that's a case of dynamic equilibrium. There's one more case given in your book. The fall of raindrop. Is it always in equilibrium? The fall of raindrop? Yes. Correct. With terminal velocity. So what about terminal velocity? Till it reaches terminal velocity, its velocity is constantly increasing. Okay? So when the raindrop initially begins to fall, before that it had zero velocity. When it falls, it is pulled due to Earth's gravity. But then it encounters, so weight is pulling it down, right? The air upthrust and the frictional force due to air drag. These two forces are acting in the upward direction. As the velocity of the raindrop increases due to acceleration, the frictional air drag also increases in the upper direction. There comes a situation when the weight downwards and the sum of the upthrust and the air friction, okay, it becomes equal. Then the net force becomes zero. So once the net force is zero, there is no acceleration. Then that highest velocity that the raindrop has acquired before the equilibrium is called terminal velocity, the last velocity. Okay, that's why it is called terminal velocity. Is that clear? So what are the forces acting upwards? So this is the raindrop experiencing mg, and upward you have. It is also called viscous force. viscous viscosity and the buoyant force. So when mg is balanced by this happens. This means so this is the net force zero situation. When this situation is encountered, then the raindrop goes with constant velocity Vt. Vt is the terminal velocity. Vt. Understood? Why the smile Vt Victoria terminus? Okay, it's V terminal. All right. What about planets revolving around Sun? Not equilibrium? What?
So, for example, it's point rate,
Huh?
it's closer to the sun, the acceleration increases because of the gravity. And when it's farther away, the speed is
So when you study Kepler's laws, yes. Kepler's laws. KEPLERS. But not before that. So right now for you, all the planets are moving in a almost circular orbit. So this is true for the elliptical orbit. But this ellipse is very minor ellipse. Okay. So for approximation sake, yes, this is also a case of dynamic equilibrium. Are you experiencing jerk while you are traveling on planet Earth? Is it equilibrium or non-equilibrium case? It is equilibrium. Likewise, as long as the motion is uniform circular motion, okay? As long as the motion is uniform circular motion, then it can be treated as dynamic equilibrium, like electron revolving around nucleus of a stable atom. Is also a case of dynamic equilibrium. Then there is one example given: a stone tied to the string, and you are whirling it. Okay, you're whirling the stone with uniform speed. So many examples. Okay. All right. With this, we come to the topic called principle of moments. Any question with regard to equilibrium? Yes. Any question related to equilibrium? Are you in equilibrium? Are you all in equilibrium? Okay, good. That's a stable state. Okay, next. So when the equilibrium is disturbed, in a fight situation. Fight situation is chaotic. Okay. So this is a stable state, equilibrium state. All right. Next is principle of moments. So what is principle of moment? It is also a case related to equilibrium. So if you take, for example, a beam balance, a physical beam balance. These days we only see it in the lab. Do you get to see physical beam balance anymore? On the shops, we have electronic beam balance with digital figures, okay, printed. But on some fruit vendor shop, you might still see it. Have you seen it? Yes. Okay. Otherwise, in laboratory, you will encounter it. So, what is the physical beam balance? On one side, you have a one side you have slotted weights. And on the other side, you have a pan where you can keep any stuff that you want to weigh. Correct? So when do we say that weights are equal on both sides? When the beam is horizontal. So the horizontal position of the beam signifies equilibrium. Why? Because the anti-clockwise torque will be balanced by clockwise. Right? When both the weights are equal, this is the pivot, this is A and this is D. AO is equal to OB, and when the weights are same, let's say this is W1, this is W2. So when will it be said to be in equilibrium? When AO into W1 will be equal to OB into W2. Correct? Which means the anti-clockwise moment is equal to clockwise moment. Right? In a general situation, let's say it is not a beams, some rod pivoted at the midpoint, and there are some more weights hanged. Let us say this is W3 and this is W4. We have hanged multiple weights. Still, if the rod is horizontal, again this is in equilibrium. Then what is this situation now? This situation will be, let's call this as C and this as D. So what you'll have? You'll have AO into W1 plus CO into W3 is equal to OD into W4 plus OB into W2. Correct? So what is it? This is sum of anti-clockwise moment is equal to sum of clockwise moment. This statement is called principle of moments. And you can verify it experimentally like this with the help of a beam balance. Okay. So if this beam is calibrated, so you can easily note down, let's say it is a meter rule. The meter rule is calibrated. The midpoint will be 50 centimeter mark. So wherever are these weights hang, you can actually, let's say there is a provision to slide it. So for various combination, you will find out that equilibrium condition is always defined by this state. The sum of anti-clockwise moment will always have to be equal to sum of clockwise moment for the beam to remain in equilibrium. Is that clear? So what is principle of moments? Principle of moment is, it states that in equilibrium, sum of anti-clockwise moment is equal to sum of clockwise moment. Okay, and this is the verification. This is how it is verified. This is how you can experimentally verify it. The beam will be horizontal always when this is observed. Okay. So this you can erase because now the diagram has changed. This is applicable. It is applicable for a single weight or multiple weights on both sides. As long as the beam is horizontal. So principle of moment will say this. All questions you'll get on this only. So how many formulas we have studied in this chapter? Only two. Okay. One is this. What is the other one? This. The formula for torque. So ultimately only one formula. The next one is only the statement using that. So only one formula. Moment of force. Okay. The next topic is, I said we'll discuss center of gravity. What is center of gravity? Already studied in 9th standard. Right? While discussing Archimedes' principle. Center of gravity, center of buoyancy, you're familiar with all that. What is center of gravity of a body? The center of gravity of a body. You recall? The CG of a body is a point at which its entire weight is assumed to be concentrated. This is the CG of the body. CG of a body is a point. First of all, it is a point at which its entire weight is assumed to be concentrated. Right? So, what is its significance? Let us say I know CG of this book. Okay. So, CG of this book will be at some point. So, if I know its CG, then I can balance that book at that particular point. I will rest it at one point. So, by trial and error method, I will find its center of gravity. Somewhere. Okay. So, it is resting at one point. So, what does it signify? Is the book at rest? So, that means net force acting is zero. So, what are the forces acting? The weight downwards and then the reaction from the tip of my finger. So, when is it possible? It's only possible if the entire weight of the book is acting at one point. That is at the tip of my finger. Is the book turning left or turning right? No. So it is also obeying principle of moment. Because book has mass distribution this side also. and this side also. It is consisting of the paper molecules on both sides, right? So they will have its own weight. So weight exerted by paper molecules on this side is balanced by the weight exerted on this side. Correct? So this is a perfect case of equilibrium. Why it is in equilibrium? Because I am resting the book at its CG. Is that clear? When the CG goes out of support point, then what happens? Unstable. Okay? So knowing center of gravity of the object, you can build stable design. So let's say you have a car and a bus. What can negotiate a curve at a higher speed? A bus or a car? Car can do that. Why? Because car is flatter, so its center of gravity is more closer to the surface of Earth. If it is a bus, right? Now its center of gravity will be at a height as compared to the car. Now the bus, when it is taking a turn, right? It will turn like this. So what happens now? Now the tire of the bus, okay? As long as the CG is between the tire, between the two tires, left and right tire, the bus will be held to the ground. But while turning at a high speed, bus will be tilted like this. If the CG goes out of one of the tires, then it will topple. So center of gravity, knowledge of center of gravity signifies stability. What is the more stable configuration? When the CG is close to the ground. Because at CG the entire weight is active. And like for us, where is the CG? Somewhere in this area, the groin area, right? Like cut me completely along the axis. So inside here and here, okay, at that intersection. Now, as long as the CG is between the foot, I am stable, right? Now, how far can I lean like this? As long as the CG is within the toes. Moment I cross, I have to fall. Understood? So CG, knowledge of CG gives us a stable configuration. Is that clear? So having known what is CG, now we have to become familiar with center of gravity of certain symmetric bodies. Okay. So one body is the rod. Rod. So where it will be? So it is a uniform rod with a uniform thickness. So rod is something which has only length, no thickness. That way you can assume. It's a linear body. So it is at the midpoint. Where is the CG of a rod? Midpoint. So what does this mean? If the CG of the rod is at the midpoint, then what does it tell you? Tells you this. The entire weight of the rod is acting where? At the midpoint. So the weight of the rod will act here. Understood? That means the entire rod can be balanced when you are providing or holding it at its CG. Clear? It will find application in solving numericals. So just remember this. Where is the entire weight of the rod acting? At its midpoint. Now, second, ring. What about ring? It is a symmetric object. For all symmetric object, the CG is at the geometric center. Okay. So this is also symmetric on the left and right of the center or midpoint. So this is at the center. Is it on the body or outside the body? Huh?
Outside.
Outside. Is it lying on the body? Like in case of rod, it was lying on the body. It is not lying on the body. Okay. So in such situation, suppose this is a ring and there is a nail here. This is where you have suspended. Let us say the ring is suspended on the nail on the wall. So the CG will lie just below the point of suspension. Understood? So this point of suspension has to be above the CG. Is that clear? So how do I balance this ring now? Now the tires of the bike, it has spokes. The weight of the tire of the bike is in the rim. It's outside only. The weight of the spoke is negligible. Okay. So where is the center of gravity of the bike? At the center. Now you can hold it at the center. Understood? Okay. So that could be a case of ring. Because otherwise you will say how to support at the center. So either you tie some thread, etc. Then you can see that you can support them. Okay. Some nylon threads are tied anti-diametrically opposite ends. Then you can balance the ring at the center. Then you have disc. What about circular disc? Again, it will be at the center. Circular disc will be, where is the CG? At the center. So this is on the body. What is making you smile so much? Is it okay? Yeah, you. Are you understanding it? Huh? So center of gravity for the disc is on the body and at the center. Okay. Now, next. What about solid or hollow sphere? Solid or hollow sphere, it will be at the center again. So for sphere, you can show it like this. This is hollow sphere. And for solid sphere, again at the center. Sometimes the questions are asked, you will be given the shape of the object and we asked to write where is the CG of this object. One more shape is, these are all 3D objects. You also have some 2D objects. Am I going too fast or it's okay? Okay? All right. Fifth is for a hollow cone. So the hollow cone will look like this. So where should be the CG? So it will be obviously in the area or region where more weight distribution is there. Right? So it will be closer to the ground. So if this is the height, let's say this is the height of the cone. So for a hollow cone, it is at h by 3, 1/3 of the height. This is the full height. So where is the CG? 1/3 from ground. So this is 1/3 from the ground. Okay. H by 3 from CG at from the base of the cone. Now 6, solid cone. Yes, it will be even closer to ground. Okay. So for solid cone, it will be. So this is a solid cone. This is at h by 4 from base of. So which is more stable configuration, hollow cone or solid cone? When you try to topple, right? This can be toppled, like this will topple after a greater angle, whereas this can be toppled easily for a smaller angle. So this is a more stable configuration, right? Closer the CG to the ground, more stable the object is. Then you have, you may have rectangle, parallelogram, or rhombus. So these are plain two-dimensional objects. The CG is at the intersection of diagonals for all such objects. Okay. For rectangle, parallelogram, and rhombus. This is at intersection of diagonals. These are all regular shapes. All of these are regular bodies. What if you have some irregular lamina? Lamina means like a cardboard, which is of irregular shape. Determination of CG. Irregular lamina. So lamina is like a plain sheet. Like this sun mica or a cardboard. How do you determine? Suppose you have a irregular shaped lamina like this. So this is still a regular shape. So I know intersection of diagonal. So I can judge. Okay. What about this? So the process is you drill 3 holes. Okay. And then hang the lamina or suspend it across these holes consecutively. Right? While you're, let's say you're hanging it over here. So if you hang it here, it is vertical. And also hang a plumb line. You know what is a plumb line? Plumb line is some stone tied to a string or some big metallic ball, like a pendulum. Okay. So that will always be, okay, hanging straight. Right? Now, along this plumb line, you draw a line. So you'll get a line mark for this hole. Now let us say this next hole was here. So now the book will tilt like this. Okay. So first line was like this straight. Now the plumb line will still hang straight. So now you draw the next line. So now these two lines will intersect. right? Again, you suspend the irregular lamina by the third hole and again draw the line. So it will again intersect at the same point. Okay, so that point of intersection is the CG. So this is how you will figure out the CG for a irregular lamina. This. So you'll require a plumb line. The impressions of the plumb line. We at the intersections of the plumb line pressure. The irregular laminas. And suspended. Let's call this as A, B, and C. So how can you get the impression of the plumb line? Plumb line will hang straight. So you can actually have some colored powder. The string, you have some colored powder. And now you stretch the string and leave it. So it will go and hit the board. Okay, you must have seen this. The construction workers often do this. Okay, so you just hit it, or while laying the line on the ground, this is done often. So the string is soaked into some colored, whatever called, some color or some chalk powder, colored chalk powder, or some lime powder. Okay, what is it? Chuna bolte hain usko. Limestone, the crushed limestone with a different stain or different color. When you stretch the string and leave it, it will leave an impression. So either do that or draw a line, whatever. So this is how you will be able to determine the CG of a irregularly shaped lamina. So any questions here? So we have some 20 minutes, little over 20 minutes, and we'll do some numericals now. If you don't have any questions.
So, the good question. So we can get the holes anywhere in the.
Anywhere. But around the periphery, near the edges. But otherwise, anywhere you can do that. Yeah. Chalk powder अगर नहीं भी है तो suppose you are suspending it at this hole, ठीक है? और यहीं पे you also suspend a plumb line. So you draw a line along the plumb line. You can do that also.
You were saying you will apply some dye or chalk or something.
Yes, on the plumb line string. Plumb line string.
And if we suspend that thread, then it imprints the line.
It will imprint only when you slightly stretch and leave. Like a guitar string. It will try to go back to its original position, right? So plumb line has to suspend downward only. But when you stretch it, it is little tinted. When you leave it again, it will go and hit the wood. It will leave an impression. Impression thing is, I have given you in the book, they have said draw the line along the plumb line. So do that. Plumb line impression. Press on the impression. Intersection of the plumb line impression on the OVG. Okay, now it makes sense. Impression, yes. This time you want it on. It will run at full speed. Huh? There is no speed control. Okay, let's begin some numericals. Odd order. Let's do some numericals. So in my book, the values and the entire numerical may be different. Okay, so if you have the new book, you can tell me. I have Selena, but the numericals done from any book, you should be able to do it because formula and the logic is same. Okay. So, or you could refer to your volume also, UT volume. So that will be common for everybody. Do you have UT volume? Yeah. What is the first numerical in that? Just give me one volume. There's everybody has volume. Come on, page number 14. So there are classwork numericals on page 14. Okay, let's do classwork numerical. Everybody has UT volume? Okay, so classwork numerical 1. So what is given here? And that is opened by a wrench of length 10 centimeters. If the least force required is 5 Newton, find the moment of force needed to turn the nut. So wrench length given is given. What is given? The perpendicular distance was OK for us. That is given as 10 centimeters. Right? The length of the wrench is nothing but the perpendicular distance from the pivot. So this you convert in meter. This will be 0.1 meter. If the least force required is 5 Newton. So also given F is equal to 5 Newton. And what is the moment of force? This you have to find out. Okay. The solution. P is equal to OA into F. This is 0.1 into 5. So that should be 0.5. Correct? So the only one formula in this chapter is OA into F. You just have to figure out from the given question what is OA and what is F. And if it is coupled, then you have to do it twice for both the forces. Okay? Or calculate the total distance between the two forces and multiply by one force. Okay? So everybody understood question 1? Next. In second question, we have a diagram. You have a wheel. This is the axle. Force is applied here. This is D and A. This is force is how much? 2 Newton. diameter given is, what is this distance? 2 meters. So till O it has to be 1 meter and 1 meter. Total is 2 meters. Correct? So first case, you have to find out torque at point O. So when O is the pivot, this is the force, then the torque will be how much? This is the pivot now in the first case, torque at O. What is the perpendicular distance from O? 1. So this will be VO into F. So this is 1 into 2. That is 2 Newton meters. So can you here give the sense of direction? In this case, you have to mention the sense of direction. So it will be clockwise. So wherever possible, you have to give the direction also. Second case, what is the torque about A? So wherever you have to find the torque, in this case you have to find it about O. So this becomes pivot. Now you have to find the torque about A. That means A is now pivot. So the perpendicular distance from the pivot. Okay. So this will be now dA into F. Because this is the line of action of force. So the perpendicular distance from A is 2 meters. Got it? That you have to always keep in mind. This is the line of action of force. The perpendicular distance from there till the pivot. This is what 4 Newton meter clockwise. Understood? So try the next question yourself. So this is given here. Yes, some crisis at the back. Huh? Some non-equilibrium situation building at the back. What is the moment of forces now? Not moment of force. What is it? Moment of forces. Find the total moment. Where is it pivoted? It is pivoted about O. What is total moment of force? Take this as F1, this as F2. And both are turning it anti-clockwise, right? What it will mean? That's why this is area. This AO 2 into 10 plus 2 Okay. What is it? 20 plus 20. 40 Newton meter anti-clockwise. In a question with a diagram, you have to always give a sense of rotation, clockwise or anti-clockwise. Otherwise, your answer will not be treated as complete. And in the book, the answer given is wrong. Okay, so it's a typographical error. It has to be anti-clockwise. So there may be some situation where you have typographical error in notes as well as in main textbook, but not very frequently in the main textbook. But here you may. Okay, be careful. Okay, question number 4. This question 4. Okay, question 4. It is a meter rule. So we have a meter rule. It is pivoted at the midpoint. So meter rule has marking 0, 50 and 100. What does it say? A weight of 50 gram force is suspended at one end of it. Let us say the 50 gram force is suspended at left end. This is where the 50 gram force is suspended. At one end. Where a weight of 100 gram force should be suspended to keep the rule horizontal. Now, if I suspend the 100 gram force here, obviously this will become more. And a clockwise movement will be more. So this will be not in equilibrium, it will be tilted. But what the question is asking? Where a weight of 100 gram force should be suspended to keep the rule horizontal. Obviously, it should be at half the distance, right? Because the product should be same. So we have to balance the anti-clockwise movement with the clockwise movement. So the weight should be somewhere here. We don't know. So since we don't know, we will take this as X. Where the weight should be suspended, we don't know. So we're taking that as X. Right? Now since finally the rod should be horizontal, so that means rod is in equilibrium after suspending 100 gram force. So at equilibrium, what can you apply? You can apply principle of moments, right? So at equilibrium, for horizontal position of rod, by principle of moments. The anti-clockwise moment must be equal to clockwise moment. Since there is only one weight, so there will be only one moment. not sum of moment. What is anti-clockwise moment? So this is 0 to 50. So this must be 50 centimeter. What is anti-clockwise moment? 50 centimeter into 50 gram force. This will be equal to, we don't know, x. So you don't write the unit of unknowns. X into 100 gram force. So you have to find the position of this, so that therefore x is equal to gram force cuts gram force, 50 cuts 2, this will cut 25. Suppose x is equal to 25 centimeters. So if this distance is 25, that means this will be 75. 50 plus 25 will be 75. So in the question, the 50 gram force is suspended at one end, then 100 gram force is suspended 25 centimeter from the other end. Okay, that is 100 gram force is suspended. It's already suspended at 25 centimeter from the other end. Okay. So is it time? So just 1 minute. So we'll wrap up today's session. If you have any questions, you can ask. So are you getting the feel of it? So try questions from your own textbook, respective textbooks, and you can ask me in the next class. Nobody has any questions, right? Okay.
Thank you.